So we already know that a subset of Rn is compact if and only if it's closed and bounded. And we also know that metric spaces are sort of a generalization of Rn. And so we might wonder whether that theorem is still true for a general metric space. And we're going to show here in exercise 7.19 that only half of the theorem is true, only one direction. Okay? If we have a compact subset of a metric space, then that subset is closed and bounded. But we're going to find an example of a subset of metric space that is closed and bounded but not compact. Okay. So up here is just a reminder of what a bounded metric space is. Right? Basically, the distance between any 2 points is less than or equal to some constant mu. Okay? And here are a couple theorems we're going to be using. Theorem 5.12, every metric space is Hausdorff, and theorem 7.8. If we have a compact subset of a Hausdorff space, then that subset is also closed. All right, let's give part A a try. So suppose A is compact in X. Then, well, here's where we use the theorems, right? Since X is metric space, it is Hausdorff. And since it's Hausdorff, and we have a compact subset of it, we get that A is closed. All right, so that wasn't too hard. A little bit more work to show that A is bounded. But it's pretty much the same proof as you'll see in the textbook for Rn. Okay. To show that A is bounded, we form a clever open cover of A by taking, well, here's the idea, by taking larger and larger open balls about some point of A. Okay. I could probably have gotten away without putting that sentence in my proof, but it gives you an idea of what's up. So let's go ahead and do it. Let's take any point A in A, and going to define a collection of sets O to be just what I said, the balls about A of radius n, where n is any positive integer. Okay. Now, I claim that this O is an open cover of the set A. Okay, it's certainly open. I mean, each set in is certainly an open ball, but why does it cover A? Well, since for any x in A, the distance from A to x, well, it's some real number, right? And you can always find a positive integer bigger than it, right? It's less than some positive integer n. Okay, and that means that it's in the ball about A of radius n. Okay, so for that reason, the collection O is an open cover of A. Good. Well, here's where we use compactness of A, right? Since A is compact, this collection O has some finite subcover, which I will call, well, it has a finite number of these open balls, right? So just pick finitely many integers. We'll do n sub 1 all the way up to n sub k, whatever k is. Okay. So we've got this finite subcover. And, okay, well, look, one of those is biggest, right? And all the other ones are contained in the biggest one. And it's a cover of A, so for every x in A, the distance from A to x is less than or equal to, well, whichever of the n sub i's is biggest, right? The maximum of n sub 1 to n sub k. So we've shown that A is bounded. Okay? So it is, it's both closed and bounded, which is what we wanted to prove. Okay. Now let's do part B. Let's provide an example that shows that we can have a metric space, a subset of metric spaces closed and bounded but not compact. And the idea here is just sort of pick a metric which doesn't get too big. Okay, so that the entire space is going to be bounded. And I also want there to be an awful lot of open sets. So I'm just going to take sort of the discrete metric, which induces the discrete topology, and well, you'll see how it works out. So consider the metric space. Really, I could take any infinite set here. I'll do the integers for simplicity. Okay, with the discrete metric, which remember is like this, right? The distance between any two integers is going to be 0 if they're the same and 1 if they're different. Okay. And this space is certainly closed in itself, like any space is, right? And certainly bounded, right? The largest possible distance between any 2 points is 1. So it's closed and bounded, but if we look at the open cover O consisting of all the singletons, okay, so the set consisting just of n for every integer n. Let me say again what that is. That's consisting of all single point subsets of Z. Well, it's open because the discrete metric induces a discrete topology, so all the single point sets are open. Okay, and it certainly covers Z, right, by design. But look, it has no finite subcover, right? If you only kept finitely many of these open sets, you would only have finitely many integers in their union. Okay? Certainly don't cover Z. So we found an open cover with no finite subcover. That means that this metric space Z, the discrete metric, is not compact. Okay? So kind of a strange example, but it shows that even if you have metric space closed and bounded, it doesn't need to be compact.